name is Chantel, and in this video, I'll be going over the signal agent. The signal agent is a Verilog task, or VHDL procedure, that allows designers to monitor and drive VHDL signals from any VHDL block, or to update Verilog or VHDL objects from Verilog code. This can be useful in testbench development and design verification, especially in mixed designs where Verilog and VHDL code need to interact, knowing that VHDL does not allow hierarchical references. So in times where hierarchical references in Verilog need to point to a VHDL object, the signal agent is there to help. Now, how the signal agent works is simple. It joins the source signal with the destination signal. The source signal drives the destination signal as if they were directly connected in the HDL model. The signal agent only needs to be called once, and from there, whatever changes occur on the source signal will carry over to the destination signal. So now, to use the signal agent, there are two different ways to call it depending on the HDL language used. In Verilog, the syntax starts with a $sign followed by signal agent, and following that are three parameters in parentheses. In order from left to right, the parameters are the quoted string specifying the path of the source signal, the quoted string specifying the path of the destination signal, and lastly, a 1 or 0 for displaying a message in the console that the signal agent task is called, where 1 allows for the message to display, and 0 quiets the message. The syntax for VHDL is very similar, with the difference being that it does not need the $sign preceding the signal agent declaration, and it uses forward slashes as the hierarchy separator. In addition to that, the ALDEC library and the ALDEC signal agent package use clauses need to be declared in the VHDL design file in order to use it. Now that we know what the signal agent is and how to instantiate it in code, I'll demonstrate it using an example design I pulled from Rivera Pro's examples folder called Bidirectional Mixed, where bidirectional is shortened to BIDIR. This example design contains only 2 units. One of them is the top-level unit VHDL entity called top, and the other is a Verilog module called Verilog unit. This example design is meant to demonstrate the exchanging of signal values between these 2 units in both directions. To show this, the example design calls for the signal agent procedure inside of the top VHDL file. Notice the ALDEC library and the ALDEC signal agent package clauses. There are 6 lines of the signal agent being called. The first 4 are to declare the bidirectional connections between the 2 units' scalar and vector signals. The last 2 are to connect the semaphores so that the 2 units can send their values over without the risk of a race condition occurring. The scalar and vector signals are first initialized with z values. From there, the process in the top unit forces the VHDL signals to communicate first using the forcing semaphore signal. With the forcing signal from the VHDL unit set to 1, the forcing VHDL signal in the Verilog unit is also 1, allowing for the VHDL file to assign S and SV signals their respective values of 0 and 55 in hex, and then 1 and AA. With the W and WV signals connected to S and SV respectively, the W and WV signals from the Verilog unit will also change to these values. Then, the top VHDL unit releases the signals and sets the forcing signal to 0, meaning that now the Verilog unit code can run. Now the forcing signal from the Verilog unit is set to 1, and that means the forcing Verilog signal in the VHDL top unit changes to 1, suspending the VHDL code until forcing Verilog changes back to 0. Now the Verilog unit assigns its scalar and vector signals 1 and hex 33, and then 0 and then hex CC. And since this is bidirectional communication, the S and SV signals from the VHDL top unit should change to these values as well. Then the Verilog unit releases the signals and semaphore, switching the control back to the VHDL top unit. And from there, The last thing it does is set forcing to 1 again in the VHDL code, and assigns the same signal values as before. Without the signal agent, the Verilog unit would not be able to access the VHDL's scalar and vector signals when it wants to update them, as the reference to them would be something like top S or top.sv, which is not legal since VHDL doesn't allow for hierarchical references. So now that we understand how the code works, let's run the macro and check to see if the values appear as expected. I will be using a macro file where it compiles the two files with the debug parameter, initializes the simulation with the VHDL unit as the top-level unit, adds the signals from the units to the waveform viewer, and finally runs the simulation for 85 nanoseconds. I'll go ahead and execute the script. And now we have our simulation results on the waveform viewer. As expected, the VHDL forcing signal being 1 allows for the S and SV signals to be 0 and 55, and then 1 and AA. And we can also see that the Verilog's W and WV received the same values. Then the signals get released and go back to their Z values, and the control goes over to the Verilog unit as intended. It can be seen here that now the Verilog unit's forcing signal goes high, and now the signals W and WV are forced their values, which also gets transferred over to S and SV. W and WV are then released, and forcing goes back to 0. And you can tell they were released by these tiny red marks, and this also indicates the switch in control from the Verilog unit back to the VHDL unit. And as expected, the values from the VHDL side are sent again, with both units' signals receiving the same values. And this is all working as intended, thanks to the signal agent. Now I'm going to end the simulation, and just to further demonstrate the importance of the signal agent, I'm going to comment out the two signal agent lines where the Verilog unit signals are the source signals. And from here, we can predict what will happen when I run the macro again. Notice now that the S and SV signals from the VHDL side are stuck at Z values when the Verilog unit takes control and forces the W and WV signals to change. Because the W and WV signals aren't called as source signals for the S and SV signal, those two remain unchanged. But the W and WV signals change along with the S and SV signals, since the signal agent is still called for them as the source signals to the W and WV signals. And that concludes this demonstration of the signal agent. Whether you're creating a mixed or uniform design, this is useful for any time you want to drive or monitor a signal from anywhere in the design hierarchy. If you need a reference on the signal agent, you can go to Help, HTML Documentation, Product Help, and search for Signal Agent. Thank you for watching.